All right, so thanks a lot, everybody, for coming again in the second series of these webinars that we're doing with RainHub and the UK RAS-led robotics task group. Today, I'm very happy because we have, I think, three amazing talks that I'm going to introduce one by one. So I think the whole slot is for 1 hour, the whole webinar. Please, whenever you have any questions, please type it in the chat. So we're going to ask the speaker after the end of his talk, not in the end of the whole webinar. So please go ahead and type your questions in the chat, and we're going to moderate it with Mercked. All right, so with this, I will just stop sharing my slide. It was very fast. So, and I will hand it to David Megson Smith from University of Bristol. David, off you go.
Hello, everyone. Can you hear me? Yes, excellent.
Yeah.
Okay, I'm David Megson Smith. I'll be talking today about our recent trip to the Ukraine, where we visited two sites with a Boston Dynamics Spot quadrupedal robot. We initially, and it's not in the title, but initially we visited a site called the Prydniprovsky chemical plant. This is the largest, or was the largest Soviet uranium processing plant in the Soviet Union. It ran from 1948 until 1991, when it was largely abandoned. This is a large industrial facility and is now heavily contaminated. It's in the south of Ukraine in a city called Kamyanska. And it's also still partly used. A lot of the buildings that weren't contaminated were sold off to private companies. So this is a mixture of a decommissioning site and an operating industrial site. 20 of the buildings that were heavily contaminated, and we were given access to 2 of these. The 2 buildings we were given access to were a building referred to as B103, which was a uranium processing factory, and B104, which originally they believed to be a thorium processing plant, and we've now managed to demonstrate that it's actually a heavy metals processing facility. I'll focus more on the robotic stuff we did. I'm only going to cover this briefly because the majority of this talk's on Chernobyl. But these were large concrete structures spanning 4 to 5 floors at times, and they are strewn with rubbish, as you can see. Let me get the little pointer up. As you can see, they are absolutely chaotically strewn with rubbish and debris, and a lot of the pipework and structures have been illegally removed or decommissioned, as the Ukrainians like to refer to it. Within a lot of the vessels, there are very high levels of contamination, exceeding millisieverts at times per hour. And throughout all of the buildings, there is a low level of dust contamination, which is quite important for a spot, as I'll come on to in a minute. So what we actually did is we integrated a gamma spectrometer on spot on this little gantry system you can see here. The reason it's on a gantry system is so that we've got clear line of sight to the ground without spot actually becoming an occlusion to the sensor. And we found that generally Spot was very well suited to the environment. He could walk around well, there weren't any particular problems. The positioning and navigation algorithms were unaffected, even in the very high gamma environments. At times we were dealing with approaching millisieverts per hour rates, and this was causing quite a degree of snow noise or white sort of speckle noise on Spot's feeds, and we're worrying that the actual position and navigation algorithms might be affected by this. Equally, as we know, these algorithms are now advanced enough that the shiny or reflective surfaces didn't seem to be upsetting him too much. The one problem we did find, however, was in the walking style. On concrete, it was generally fine, but a lot of the time we're walking on less stable surfaces, either floorboards or gantries, which had a degree of bounce to them. And this, at times, had the effect of actually creating a lot of dust in the air as the whole ground was made to bounce. We overcame this by actually switching Spot over to his crawling mode, where he only ever has one leg off the floor and therefore impacts the floor less aggressively. So what results did we get? We got we got lots of gamma maps. These are just two examples of the gamma maps we got. And as you can see, we had the capability of lifting it off the odometry data directly from the Spot API, or we had an integrated GPS, but that didn't work inside, obviously, so we chose to take the odometry data. And we've got some nice radiation maps of what their distribution looked like within the building. But the majority of my talk will be on Chernobyl. As you probably know, Chernobyl was a major nuclear accident. It occurred on April the 26th, 1986. It was in fact caused by a safety test that went wrong. They were attempting to demonstrate that you could use the inertial energy, kinetic energy left in the turbines in the event of a power outage to keep the cooling rods, to keep the water running through the reactor. However, as they turned the reactor down, it started to switch itself off. To prevent this, the operators at the time, against protocol, removed 193 of the 211 control rods. There was an absolute bare minimum where you had to have 29 control rods left in for it to operate safely. And I think you can tell that the difference between 193 and 211 is less than 29. This protocol, this problem was further compounded when at the very last minute someone hit the emergency stop button, or scram as we refer to it in the industry, and this should have dropped all the control rods in. Yet a design flaw within the RBMK reactors meant that there was a spike in energy, ultimately causing a massive explosion within the reactor. Over the course of the next 9 days, 400 times the radioactive material that was released with the combined Hiroshima and Nagasaki nuclear detonations was released from the Chernobyl plant, resulting in the evacuation of a large area around the plant, referred to as the Chernobyl Exclusion Zone. There's actually different levels of the exclusion zone. There's the outer exclusion zone, and there's the closed zone, which is immediately around the plant. They're defined by the amount of contamination available. More recently, in the last decade or so, you can actually start taking tours within the zone, and as a way of trying to raise some money for their upkeep and decommissioning activities, tourism is now an element there. We've been there before. We've done a lot of drone surveys there before, but this is the first time we've taken a legged robot, a quadrupedal robot, into the zone. So, as well as doing a visit to the actual power plant, we did quite a lot of work in the exclusion zone itself, where there's high degrees of fallout. And one of the things we wanted to demonstrate is that you could use Spot for semi-autonomous. This is where we pre-programmed a loop and searching for fuel particles that were deposited in the explosion. And you can see on the top here, we have our raw results. This is our raw GPS plot of where Spot was and what the radioactive counts were. You can then do a rough linear interpolation between those points to try and get a better estimate. And then at Bristol, we've actually been developing some inverse linear inversion localization procedures, which can work backwards. And with a cautious approach, I think you might believe that there are particles here, 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 and here. And there's a contaminated actually bucket of waste up in the corner of the survey site here. So we were quite pleased with this result. We showed semi-autonomous mapping and identification of fuel particles. We then, after that, were invited to go to a decommissioning vehicle graveyard. And this is a place called, or a former village called Burya Kivkiv. And they have lots of interesting stuff there. You know, the history of the accident. They have the Soviet moon lander that was used to clear the reactor roof. They have the failed West German Joker robot that they attempted to use, but due to the actual radiation flux, failed within the first 15 minutes. They also have all the helicopters left over that were used for extinguishing the fire, and lots and lots and lots of armoured personnel carriers, all with varying degrees of radioactive contamination. And they asked us to do a general survey of the site using our equipment. One of the things we found straight away, which they were aware of, were two SARI, or waste tanks, that have been used for transporting liquid waste. These were by far the most active vessels or components we saw at either site, Chernobyl or PCHP. Over the previous 4 or 5 days, we'd actually integrated a new system onto Spot. After one of our systems had failed at PCHP, we'd stripped it for parts, rebuilt it, put it on a new pan tilt system, put some new software together, and integrated a collimated gamma spectrometer, stress it's collimated, with a camera and LiDAR on a scanning pan tilt unit. Now, the advantage here is this particular area was so contaminated, we couldn't even walk into it without our alarm screaming retreat immediately. So the only way we could actually deploy a sensor here was by delivering it on the back of Spot. The reason we had to sit him down is because we found that there's some sort of feedback within his own system, but if you ask him to stand continuously, every 10 or 20 minutes, he'll move a foot and not position himself exactly back where he was previously, which meant that you'd get discontinuities within our scans. We also did the same thing. We took a picture of the Joker robot and took a scan of that. And what you can see here is that there is heavy levels of contamination on the wheels, which is what you'd expect. And we also did some gamma mapping, gamma radiation mapping of the actual graveyard itself, which is in the top left-hand corner here. But after all of this, we were invited to attend what we were told at the time would be a boardroom meeting at the Chernobyl nuclear power plant, just to discuss the possibility of maybe deploying something at some point in the future. So we turned up and we were immediately told we would be deploying within half an hour. And was there anything we needed? And without much warning at all, when we asked what deploying meant, they said, well, can you just give us anything, any information, any scans? Can you demonstrate robotic platforms working on our site? So 2 hours and 5 radiation checkpoints later, a new set of clothes and more security than I have been through at any airport, we eventually stepped past this security checkpoint. And you can see this building from miles around, but I cannot stress to you how big this building is. This is the largest movable structure ever. Due to the contamination around the power plant, they weren't able to build this structure immediately over the power plant. So it was actually built adjacent to it and then physically moved on rollers over the power plant over the course of about 2 weeks a few years ago. It's vast. And then we walked through yet more checkpoints, put on more PPE, and walking down corridor after corridor, no one gave us any warning. We stepped through one door and suddenly you're in the building next to the reactor. And when I stress there is no warning, it's just like a corridor. There is no line of sight into the building, into the area, and you step through and you realize that you're looking at a building, a nuclear power plant inside a building. It's quite difficult to explain how vast it is. The other thing that we found very interesting was all our radiation alarms went off. They actually put the entrance doorway in the most contaminated or the most, what we call a shine path, the most active area with radiation coming directly out of the plant. We couldn't get a straight answer as to why they decided to do this. One theory that we're postulating is that it enables you to actually check your radiation sensor when you enter. If it doesn't go off, then you know you haven't got a working radiation sensor. So having set everything up, we walked through the door, all our equipment's working beautifully, and the second we step through the door, all of the connectivity to all of my the pan tilt system that we were referring to as the Yandavos totally drops out, and we lose all communication and ability to do anything. Some frantic scrabbling around, we found an Ethernet cable, we plugged it in, we reset everything, we moved it over to 5 gigahertz from 2.4 gigahertz, and I'm almost finished. I've gone slightly over, I guess. And we got some good data. We managed to do a radiation survey in and around the actual plant here, which you can see here. And then we also managed to deploy our correlated gamma scanning system in front of the western wall, where we took this survey for radiation emanating from the wall. And the reactor, the most exposed part of the reactor, is actually behind this section of the wall here. So the results we got are what we'd expect. That's about all. One of the reasons you see here is we've got these little feet on. We've got these little socks on that we had to put on. That's because the floor is incredibly dusty, once again, with low-level radioactive contamination. And we put these on so actually we could just throw the plastic away afterwards and not have to remove Spot's feet, which were the alternative that they were suggesting. I'd finally just like to say thank you to Yannick and Matt. We all worked as a team, and like I say, we had a piece of equipment fail in PCHP, which was our original correlated pan tilt gamma system. And over the course of 7 days, we went from stripping it for parts to rebuilding it on a new pan tilt system, writing all the software, deploying it and integrating it with Spot. And the Thursday after the first one fails, we've actually managed to deploy it in the Chernobyl plant. A lot of this is down to Yannick, who didn't take enough clothes and took far, far too much laboratory equipment. Next time he says he'll take a second suitcase. Just like to say thank you to Pete in particular, who did all the administrating, all the charming of all the Ukrainian officials. Yannick, Matt, Dean and Erin were all on the team with us. Tom's obviously our little master and commander back here in Bristol. And Suresh wrote a lot of the interfacing software between the gamma specs so that we could integrate them nicely. We also had an army of people looking after us and holding our hands in the Ukraine. So thank you to all of them. Thank you very much. Some tourist snaps there. I forgot I left those in. Does anyone have any questions?
Thanks a lot, Dave. That's very interesting. There are a couple of questions in the chat, and I do have a question. All right, so let me start with the last one by Luke. Can you describe the collimated camera spectrometer mode of operation, resolution, and sensor name?
Right, okay, so we had on there, we had a lead collimator around the Chromec GR1. It was on just a commercial pan tilt unit. We then actually had dual LiDAR systems. We had an Intel RealSense, one of these new solid state systems, L515, as well as a single point LiDAR system. We found that as Intel will tell you, the solid state RealSense system doesn't work too well externally due to contamination from sunlight. But the other system does work quite well. We've got up to 40 meters range on that. What we did do, and this is actually really important whilst we're out there, we adapted the scan profile, because what we found is due to constantly changing priorities and timings, we would never be able to tell we had a 2-hour window to conduct a scan or a 1-hour window. So we actually built the scan algorithm in such a way that it didn't do a normal raster pattern. It did at the lowest resolution possible, so it did a 2x2 grid, and then it filled in the gaps, so that if suddenly we had to cut a 2-hour scan short to 1 hour, we still had the whole area scanned just at a lower resolution than scanning everything at a high resolution but only having half of the scene completed. So the scan resolution is that we could leave it running as long as we wanted, and it just continuously increased the resolution.
All right. Okay. I guess there is a comment on one of the first slides about the movie Chernobyl. Is more science good if it's a journal statement? But
most of it, we were arguing about this whilst we were out there. Most of it is quite good. The really concerning bit we all had was there's the bit about the beam of light that goes, the Cherenkov radiation beam that goes off into the atmosphere. That did exist and people could see it. It should not be a correlated beam going straight into the atmosphere. The other one, the really bad bit of science in it, is when they calculate the steam explosion would be a 4 megaton explosion. I did the maths a while back and worked out about a 400-ton TNT equivalent explosion. So they're about 4 orders of magnitude out on that one. But other than that, a lot of the science is very, very good, and they've actually hit the nail on the head. There's only 2 bits where they drifted away.
All right. Okay. So there is one quick question because we have to move on.
Okay.
What happens with the data set that you collected?
In what way? What are we doing with it?
Are you going to open source it? I guess this is the question.
We'll publish it. We'll put it out there. I don't quite know. We've got all sorts of agreements with Ukrainians, so I don't know if we're allowed to open source. If we are, I think we're more than happy to do that. I'll have to check back with the team, but I've got no problems with that. But yeah, we can push that out there.
All right. One question from my side. Did you face any problem with the electronics or the telecommunication with the robot due to radiation or?
We don't think so. Like I say, the only strange thing we had was the moment we stepped out of the safe area in front of the Chernobyl plant, all wireless access from the Raspberry Pi just dropped out. But we had 2 Raspberry Pis. One kept going quite happily. The other one, which had never done it before, and it was the exact second we stepped through the door, it just died. And I tried restarting it. I tried playing around with it. Couldn't get it to work. I flipped it across to 5 gigahertz and it started working. Other than that, no. We saw some white speckle noise on the camera feeds at times for spot, but they didn't appear to be affecting any sort of positioning and navigation algorithms. So no, there was nothing disastrous we saw.
All right. There are also a couple of questions, but if you can answer them in the chat, it would be great.
Okay, I'll do that.
Because we need to move on. Thanks a lot, Dave.
Okay, thank you very much.
Thank you very much. And I would like to invite now Olivier Stasse from LAAS-CNRC. Olivier, if you can share your screen. Olivier is going to talk about a humanoid motion control and whole body planner. Off you go, Olivier. Thanks a lot.
Yeah, so thank you very much, Dimitrios and Maurice, for the invitation. So Maurice changed the title of my initial talk to Industrial Deployment of TALOS Humanoid Robot. So I try to put a bit of context with a joint lab we have with Airbus, and which is called ROB4FAM, meaning Robotics for Future of Aircraft Manufacturing. And so the point is automate aerospace industry. And well, 2 years ago, you may have found this picture on the KUKA Aerospace website. And this video disappeared, but it gives you a good insight of what were the main view of the robotic industry and how to automate airplane plans. So here you have a huge 2 tons KUKA robot holding a 250 end effector, which is here on a rail. So you have a civil engineering, which needs a lot of investment, and most of the time, which can be, which start to be interesting financially speaking after 20 years of selling planes. So, and here, given the size, you can guess which plane was stopped in Airbus, and you see those other robots inside the airplane. So the point is, I think putting robots in the industry is very difficult. You may have maybe learned that this year, Boeing removed all the robots from their lines after 7 years of testing, mostly due to the fact that the pieces that were going out of the automatic line was giving more work to the workers than it used to be. So it was a bit of a failure. So off remark was that some feedback I had is that the end effector here is getting path failure every 3 or 4 hours, which make it very difficult to use. So all of this make the fact that this big, huge automatic system that you find in the car factory maybe not suitable for aerospace, knowing that in the application they drill 125 million of holes per year, and then 75% are done manual. So for them, partial automation is desirable. But if the robot is failing, which may happen due to the fact that sometimes there are a lot of suppliers which are late, delayed, or that sometimes the plane are custom made for specific customers. So you need robots which are able to adapt to changes and need to be flexible, and at least that you can remove it if there is a problem. So for that, we have a very, very humble approach in the fact that if you look at the number of UPrime projects that have been done by a lot of very good lab, DLR and others in the European country, and that most of the times people fail to use those robots inside the real world. What we are trying to do is much more trying to build building blocks, mostly software, that we try in the humanoid robotics field as a scientific flagship, and then put it back into to transfer through pragmatic proof of concept. And most of the time, basically teaching people about interesting tools that can be used from the industry. So for example, the first time we discussed, they were telling me that you are still setting the position of the motors to plan robots system. So for them, it was having automatic tool was very interesting. So our current objective here to highlight in the project in cooperation with the H2020 European project Memory of Motion is to have what we call the kind of the 3D version of the navigation stack that you can find, the 2D navigation stack that you can find on ROS. And what we would like to have is this humanoid robot currently sold by PAL Robotics. And so this robot is a very nice collaboration with PAL Robotics. So my group and more specifically, I put a lot of input on the specification of this robot. We made a tender, which was won by PAL Robotics. And in 1 year, they were able to build this robot, which is one of the only robot that you can buy actually from a company that will provide you position control and torque control. So it's still a prototype. There is only 6 instances, but as a researcher, I'm super happy to see that this has been sold to other labs, but it's still very, very cool. And the point here is that we want the robot to be able to, in real time, find the right motion to do in this kind of setup, which was built to be able as a benchmark. So we have the 3D model that you can use and test your algorithm with, and which are representative of things that you can find in some factories. So to do that, what we have is this kind of complex architecture where basically you can find here in yellow the classical sensor part and then the action part, okay? And right now, to do all of this, you need a state estimator, you need a system to making object recognition, you need a SLAM system, motion planning. Then once you have the motion planning, you need a system defining a central dynamics, predictive control, trajectory optimization approach, stabilization, and whole body QP controller. And very often, this part is usually inside an industrial robot, closed, that cannot modify. And one very interesting thing with PAL Robotics is they have a very, as they are developing a lot in ROS, providing both industrial grade system that you can buy and ask for support, or remove them and put your own. and that a lot of things that they're providing is open source, which is good for me because sometimes we have primes and we want to go into this, and when we have closed source, it's really a pain. We develop our own system. So here we're able to develop our own QP controller trajectory. And very often what's happening is that an integrator provided with this QP controller will provide a finite state machine, which will define a sequence of motion that the robot will be able to do. What we would like to do actually is a vision is to simplify this, to have directly a whole body model predictive control, which will basically solve all of this at once. I'll try to emphasize a little bit the difficulty about having this approach. So for the finite state machine, what we have presented and done on this robot is an automatic generation here of the finite state machine that is here. So the information provided here are only the model of the robot, the fact that if the robot wants to manipulate object, he will use his gripper, okay, a set of constraints, but this is embedded into the constraints of the robot, and the object specify, so it's what we call the documented object or affordance-based object, where you specify how the object can be manipulated. You specify the affordance. Once you specify this affordance, the robot will automatically explore a sequence of constraints he has to do in order to swap the state of the box. So basically, given only this to the system, everything embedded into the robot, we can generate this current finite state machine. So, of course, we have problems. One of the problems is that we still have not the trajectory optimization. So you can see that the robot is doing a lot of strange motion. It's because we are still using a random-based approach. Right now, we are trying to find a feasible solution, not the optimal one. And I'll try to show you afterwards what kind of solution we can put to make the optimization. And we had a lot of problems due to some calibration problems we are trying to solve with PAL robotics. So basically here, it couldn't work if we didn't have visual servoing working, where the robot will correct, for example, the difference between the hand and here the system. So we could have used neural networks and very advanced computer vision system, but here we use classical markers things to simplify the problems. But here we really plan task and not only a trajectory, because right now our test didn't work on this robot. Okay, so yet to do what I told you, the classical approach we have, and I think which is shared by a lot of other groups, we have in one sense a reachability planner, which will do one thing, try to find a trajectory where, for example, the trunk of the robot, here it's a legged robot, should not be in collision with the environment. But because you have legged, you need to have contact with the environment. So the limbs has to be in contact. This is why the green part has to be in contact with environments. So once you have this trajectory for the overall system, you plan a sequence of contact provided here. And where you just remove one contact and try to find another pose of the robot where you are basically statistically stable while you have another contact. So once you have this sequence of contact, what we try to find is a central dynamics trajectory for the system. And we try to favor the trajectory where the central dynamics system will fulfill most of the constraints. And this is here, this area of the center of mass, which are the easiest to perform, or you are the farthest from some of the constraints. And when this is done, we use a classical quadratic whole body force control approach to generate the whole body motion on the here the HRP2 robot. So you can see what I've shown you is a sequence of system, and in this direction it's kind of nice. The main problem is that if each sequence just give you a necessary condition. It doesn't give you the sufficient condition. So, which means that it may fail at the end here, and then you have to go back manually actually to change to add constraints in order to make something which will be feasible by the robot. So you end up with something which as complex as this. So I will spare you this just to show you it can be complex. What we like to have is a whole body model predictive control, which would almost simplify the last third part of the system I just showed you before. In the frame of the EU Prime project, Memory of Motion, we wanted to develop this generic methodology to generate complex motion for robots in real time and apply it to exoskeleton, humanoid, and quadruped robot for inspection, as we have seen very nicely in the talk before. So our goal was to being able to simplify an architecture to perform whole body predictive control with an MPC, whole body MPC at 100 Hertz on the real robot to prepare torque control locomotion. And I will try to show you after, convince you why we need what we call memory of motion. So I go quite fast on this one. So we frame it as an optimization control where basically we have cost and constraints inside the system. And then we have the dynamics of the system, which is described. Most of the system here mix are highly nonlinear because we have contact and mix integer and continuous variable. So our first aim was to have a fast implementation focusing on sparsity and having a simplistic implementation of a differential dynamic programming system, and then inject constraints using penalty-based method because we believe that SQP with projection-based algorithm are not suited for the problems that we are aiming at. And actually, we have been able to reach a very nice implementation with code generation, which allows us to be able to work on plenty of robots. Display here, humans at LAAS, the TALOS robot, and the Tiago. And we have been able to generate very interesting motion like jumping. So just for the story, I think our colleagues from Endeavor, I think Wolfgang, I think you are a co-author, just made the TALOS robot jump 1 centimeter. So it's not a big jump, but still it's kind of nice. And you know, we can generate this kind of motion with this approach I just described. So just to give you a few numbers, we are able to achieve 50 Hertz with a 38 degree of freedom iCub, 20 degree of freedom TALOS. So everything is open source and freely available on our website. The framework is called Crocodile. And if you have a classical 6 degree robotic arm, you can go up to 2 kilohertz with the whole dynamics on an horizon of 2 seconds. So we did the experiments on the real robot here. So this was done at the TALOS robot of PAL Robotics, which are also our partner in H2020. And I think Francesco is here. So if you want to ask a specific question to PAL Robotics, you can maybe answer them. So here you can see that the robot is in torque control. You can see all this motion. You can interact with this robot, which is extremely powerful. We made experiment where I can lift up to 35 kilograms, so it's extremely powerful. Still, you can here directly interact with the robot thanks to this system. And we just submitted a paper when we do MPC state feedback on the robot, but without locomotion yet. Okay. So I think we are very happy about this. I think as far as we know, whole body state feedback MPC was not done before, and it took us 8 years before doing this. And it was thanks to the collaboration that we had with PAL and working on the fundamental algorithm built in collaboration with them. So in terms of torque control locomotion, I'll try to go yes, show you directly the video here. This is the first experiment, again, done by PAL mostly. So this is here their whole walking system. And here they are using our walking planner, which is basically able now to plan not only quasi-static step, but also dynamical transition between steps. So it may be nothing, but here you can see that the robot is sometimes slightly colliding with some of the tile. And if you don't have if you have a position control robot, this is triggering a fall. So most of the fall, for example, inside the DRC, were due to the fact that the perception was slightly off. And then when the position control robot hits the tile, then the system is not able to recover. Here, I think this is interest of the of having the four-star controller robot. And again, here I think having a robot that you can buy and with a wonderful support from PAL, this is extremely difficult. I think this is the only robot which is providing this. We try to build the Atlas robot, but Mark Abbott say we cannot. I think this is a support which is a bit too difficult to do. Okay, so in the course of doing this, what we found out that there were problems due mostly to the fact that they were not able to go to high frequency due to delay between the torque sensor and the main CPU. That there were flexibility in the motor transmission and the harmonic drive. And to cope with that, we developed an open hardware project. So it's a small solo robot that you can buy for 10K. Actually, you can do, you cannot buy it, sorry. You can redo it by yourself for 10K. And this robot is able to go up to 1 meter. And we are using exactly the same algorithm on these small robots. And once this is fixed, we then move to our big humanoid robot. And we also develop our own power electronics. So I think, again, something that was discovery for us, but up to few years ago, you didn't have that much CPU close to the robot. And having really strong ARM controllers directly here at the motor level allow you to do very much more powerful control of the actuator. And I think the first one to do that were the people from University of Tokyo. So the Jaxon, the next talk will be very interesting. Show you what you can do with this kind of nice new power electronics. Okay, just one of the problems with DDP is that when you start to play with it, you have so many motion that you can generate that it's very, very difficult actually to find the right weights or to find the right formulation of the system. So what we find out is that maybe using machine learning techniques to warm start the system and have directly the warm formulation will be a nice stuff. So for this, we generate tons of motion. And what we did for that is we use it to actually warm start our trajectory optimization, which is the dual of the Pol IC optimization that you have. You can see one of the or the other. And what we did to explore this system is that we create a map. So we explore the state space, sample the sum of the optimal trajectories that we have, learn them, and use actually these neural networks, which are much, much faster than solving the optimal problems. So actually, you use it as a metric to explore your state space. And then, once you have explored all the state space, it gives you a warm start. If you learn the optimal Pol IC, the value function, and the optimal solution. Now, the point is that what happens with neural networks is very often they are an approximation. It might not be feasible, but putting this back into the DDP make it then allow you to, you can let the system recorrect it automatically. And we did this on the on a kind of playground in simulation, and this is the final results. So that we have right now. You have the robot, which is automatically decided the sequence of footsteps that he will do just by driving the robot around. And then based on that, you can find the sequence of contact that the robot should do. And then the next step for us is to try it on our locomotion stack that we have been developing with PAL Robotics on the real robot. And I think that's it. I'm almost up to the time. So thank you very much. So I think just to concern, so having this nice collaboration with Robotics, we just started a company with one of our postdocs inside the lab. Really is helping because they are very complex machines. We have to iterate over it, and this joint collaboration was very nice. We try also to stick to the application of the industry just to try to focus on the real problems. And this helped us to concentrate on the math and the scientific problem. Thank you very much for your attention.
Thanks a lot, Olivier. We don't have much time, so
sorry.
I haven't seen. No, it's not about you. It's because we go over time with questions. But I will ask you one question, and then the rest I will type them on the chat for you to answer. Okay. So one question I have is the following, and it's on your whole body controller. So we have seen from other groups that usually people try to solve a simplified potato model for solving the dynamics, and then they go into more detailed model of the robot and the dynamics to be solved. So they try to simplify first the problem, and then they go. Do you do this kind of approach, or are you going directly in solving the full detailed dynamics problem of the whole body?
So traditionally, people do that. As you're right, you mentioned it very nicely. So
yeah.
They solve the central dynamics problems. So usually with actually it was proven that you can project all the dynamics of your robot around this center of mass. Then the necessary condition is to find a trajectory for this center of mass. Now, then you put it in a classical whole body QP control, and people solve it.
Exactly.
What we found out is that very often, there is what we would like to do is to do directly this on the future. And why you have to do that is very often what's happening is that specifically when you start to climb stairs, it's a bit complex because you start to have the interplay between the dynamics, the kinematics, and the collision, and all of this make it very complex. So if you just consider the first stage, and then you add it, very often you end up at not being able to do the system. Okay, so something a bit. So what you can do is it was proposed by Kojima, is a dynamic filter where you do first projection and you correct your center of mass, and when you find out is in one iteration it works well. But if you want to generalize it for not only the dynamics but collision and so forth, there is no other way around to go into this direction. And Emo Todorov, we honestly we thought it was impossible until Emo Todorov come in and say, "Wow, guys, I can solve this problem by simplified." So we started to look into this, and so we're not as good as Emo Todorov because he's able to find the contact. We assume that the contact are given, but given the contact, we are able to find this nice trajectory for considering the whole constraints.
All right. Okay. Thanks a lot, Olivier. I will ask the rest of the questions in the chat. So thanks a lot again for the talk.
Thanks for the invitation.
Yeah. Nice. So now let's move to the last talk. Sorry, we will be slightly delayed. The last talk is from Kunio Kojima and Yuta Kojio from University of Tokyo in Japan. And I saw in the room also Professor Inaba, Kakyuchi, and Okada, which are from the same lab. So thanks a lot for joining our webinar. And you will talk about the Jaxon robot design and locomotion. Whenever you're ready to...
Okay. Can you hear me? Okay. Now we are going to talk about the hardware design and the locomotion system of Jaxon series. And in the first half, we talk about the mechanical comparison of Jaxon 2 and Jaxon 3 and the low-level joint torque control system. And in the latter half, we talk about the whole body balance control, the footstep planning, and the system integration of walking control and vision recognition. And these are Jaxon series and its previous model. As you know, the left robot is shaft robot S1, and it participated in DRC trials. And its most important feature is the water-cooled motor system. And the system is also used in Jaxon series and contributes to its high torque and high speed performance. In Jaxon series, some features are added: anti-impact armor and optimal body proportion. However, the old Jaxon's impact mitigation performance was limited, so they could not run or jump and could support only one-time fall-down impact. So, on Jaxon 3, we adopted a new drivetrain system and a new frame structure. And it has obtained high back drivability and lightweight body. And now it achieved dynamic motions like jumping. Specifications of Jaxon 2 and 3. The drivetrains of Jaxon 2 and Jaxon 3 are almost the same. In fact, the differences of gear ratios and the maximum torques are under 5%. However, Jaxon 3's weight is 50 kilograms smaller than Jaxon 2. The main contribution factors are electric device and frame structure. About electric device, this new tiny motor driver is about half the size of the old driver. And water coolers of the drivers are also downsized, so their benefits are not negligible. And the frame structure's contributions are more significant. Jaxon 2 joints have rotary actuator, so large bending stress occurs at the proximal part, and Jaxon 3 joints have linear actuator. So the bending moments are resolved into actuator's tensile forces and frame's compressive forces. This effect reduces the bending stress and saves robot weight. And about drivetrains. Jaxon 2 has modular design joints. And the joints consist of timing belt transmission and harmonic drive transmissions. And on the other hand, Jaxon 3 has a custom design joint. And the joint consists of gear transmission and cable pulley transmission. And in Jaxon 2, output transmission stage is harmonic drive. So the video shows the free fall motions of Jaxon leg. We can tell that the joints have large viscous frictions. And in Jaxon 3, the output transmission stage is cable pulley transmission. So the joint achieves high back drivability. And this is the low-level joint torque control. Our joint torque control is based on torque loss compensation without torque sensors. Whole body balance controller decides the reference joint angles and torques at 500 Hz. The torque-less compensation is implemented on the motor driver level. And we estimate torque loss from motor's rotor inertia and viscous friction at 230 kHz. And then we compensate the estimated torque we compensate the estimated torque at 1 kHz. And our torque control system does not use torque sensors and does not depend on the sensor's SN ratio. And it achieved low latency torque feedback loop. And this hardware and low-level control system enables Jaxon to achieve these motions. Jaxon 1 and Jaxon 2 have high torque and high speed performance. So, and barbell weight used in squat motions is 70 kilograms. And Jaxon was able to continue 39 times squat motions until the motor temperature achieved the limitation. And as high-speed motion, 10 swing motions are very famous, maybe you know. And as another high-speed motion, Jaxon 2 achieved skating motions. This is roller skating motions, and this is skateboard motions. And then Jaxon 3 have high impact mitigation performance and achieve dynamic jumping motions, like videos. Maximum COG height is currently 0.3 meter, and the robot stayed in air for 0.5 seconds. And next, the latter half part, this is the overview of our locomotion system. Working and balance controller generates the reference GMP and COG trajectories based on vision information and actual robot states from the state estimator. And the state estimator removes the sensor noise and drift by using some filters, like carbon filter. And the generated GMP and COG trajectories are transformed into joint angles and torques through wrench distributor and whole body inverse kinematics and whole body inverse dynamics. And wrench distributor calculates the reference contact ranges from the GMP by using quadratic programming based on the contact constraints. And finally, generated torques are sent to the motor drivers.
So next, I'd like to talk about our locomotion system. Working and balance control for bipedal robots have been widely researched, especially footstep modification is effective for large disturbances. However, most of these methods do not use vision recognition and assume that robot surroundings are almost flat. So if there are walls and or ditches, which will most likely exist in their environment, the robot, needless to say, will lose its footing and fall down. And this video shows a simulation in which the robot modifies footsteps depending on disturbances and steps into a ditch. On the other hand, footstep running using vision recognition has been also researched. However, these planners do not consider robot's balance in real time, so the robot may lose balance if there are disturbances. That's why we put importance on integration of real-time balance control and vision recognition. The right video shows the footstep modification considering a foothold. The robot could maintain balance by modifying footsteps depending on foothold and balance. First, I briefly explain the walking pattern generation method. We regard human dynamics as a linear inverted pendulum model and use capture point as a balance index. We ensure the walking balance by controlling the DMP such that the middle of the supporting foot corresponds to the capture point at every step. The optimization problem for keeping the DMP as close as possible to the DMP reference is expressed like this. The important thing is the problem is analytically solved using calculus of variations, so the computational cost is very low. The lower right figure shows a generated trajectory. It shows that capture point reaches to the same position of the supporting foot at the end of double support phase. Possible range of the GFP is constrained within the support polygon. Therefore, there is a limit for handling disturbances using the walking pattern generator. At such times, modifying landing position, timing, and angular momentum is effective. The light blue region shows the capture region, which is a set of possible capture points by controlling the DMP within the support foot until the landing timing. If the nominal landing position is outside the region, the robot projects the landing position onto the region to regain balance at landing timing. The modified time and angular momentum are also calculated by using this capture region. The video shows the lateral push recovery simulation. The robot could deal with disturbances by appropriately modifying these three walking parameters. Next, I'll explain the modification method of walking parameters considering foothold. We recognize steppable regions as a set of 2D convex cells and modify walking parameters that satisfies capture region and recognize the steppable regions. The light blue region shows the capture region without the step time change, and red point indicates the nominal landing position. If the robot extends the step time, the capture region will become larger and far away from its supporting foot. And as a result, the capture region touches the steppable region. In this way, the modified landing position and timing are calculated. In addition, if both constraints are not satisfied due to strictly limited steppable region, the robot moves its upper body to compensate for the deficient step lengths. In this video, the robot was commanded in advance to walk forward on the flat floor with a constant step length. And the footsteps were automatically adjusted online based on vision recognition. So another role of vision recognition is to lead the robot to a goal position. Usually, locomotion planner for humanoid robots deals with footsteps. However, as previously stated, this kind of system lacks robustness. So in our system, high-level controller plans only a rough path such that the robot avoids obstacles. And the footsteps are determined by a real-time controller, which will make a locomotion system more robust. This video shows the path planning in an environment with stepping stones. Lastly, I'll explain our recognition system. The upper figure shows the conventional footstep planning system. Footstep planner plans footsteps using global map, in other words, SLAM, and walking controller receives footsteps. On the other hand, our system plans nominal path, and walking controller receives walking velocity and steppable regions. Additionally, we use two different maps, global and local. because both have pros and cons. Since the global map is reliable in the long term, it is suitable for a global path planner. However, localization sometimes suddenly changes, so steppable region is not always reliable. That's why we separated the steppable region recognizer from a global system, and we use a local map for the recognizer. This video shows the experiment in which the Jaxon traversed on stepping stones consisting of unsteady blocks. The robot was able to work on unsteady spread footholds with the proposed control. In particular, even though the blocks under the supporting foot were tilted, the robot dealt with the influence by modifying footsteps. This video shows a push recovery experiment. The robot started stepping based on the measured capture point and support polygon, and kept stepping until it could regain dynamic balance. The parameters were instantly adjusted according to the robot's current state. In addition, the robot changed its whole body motion so that the constraints on the steppable region and step time were not violated. That's all. Thank you very much.
Great. That's really, really nice results. Thanks a lot for the presentation. We're a bit over time, but I would like to ask one question that came up in the chat from Cheng Shu. It says, it's for the first part of the talk. So it says, how durable are the cable-driven actuation system compared to the old one? So in terms of hardware design.
Okay, it's a good question. And at first, our cable-driven system was very short lifetime. For example, 1 month. But after repairing and now about depending on joints, but about 1 year. And we changed the spool coating procedure. So by preventing spool from rusting. It was very great effect.
All right, that's great. That's great. One more question from Maurice. I think both Maurice and Oliver commented that this is a very impressive work. So the question is, what sensors are you using? Do you depend only? Are you focusing on the spinning Kojio leader only? And are you happy with it?
So I'm using RealSense.
All right. Oh, by itself? So it is only the RGB?
L5515 and the T265.
All right. Okay. That's good. I think we don't have any other questions. I don't have any other question from my side. So with this, I would like to thank you very much, everybody, for the presentations, all the speakers.